Good morning, everybody. Week 2, here we come. So how was week 1? I'm hoping it was good. Please feel free to any questions you may have in between classes, any concerns, and don't forget to hand in the homework. Again, you will be checking your own homework. However, you will be graded on whether or not you hand something in. Okay? All right. So today, what we're going to do, we're going to start with different probability models. Okay, so let's put this definition up here. Okay, so a uniform probability model, the events have an equally likely chance of happening. Okay, so I'll give you a second to copy that down. And then there's just non-uniform, and non-uniform means the events do not have. And I'm going to show you some examples of that. We'll do some examples together. With non-uniform probability models, we talk a lot about, we discuss the odds of events occurring. Okay, so we're going to take a look at a short video about this, and then we'll do some problems.
The probability of landing on red, I know that there are, and on, one of them is red. So the probability of landing on red is 1/4. This is my theoretical probability. Probability of landing on blue, again, there are 4 equal spaces. One of them is blue. So my probability of landing on blue is 1/4. Thing, it is 1 out of the 4 equal spaces. Purple is also 1 out of the 4 equal spaces. Since these probabilities are exactly the same, this shows a uniform probability model. Other things that are going to be uniform probability models that you're going to see frequently are flipping a coin. Heads and tails each have a 1/2 theoretical probability. A normal 6 or number cube with the numbers 1 through 6, they all have an equal probability. It is a uniform probability model. So now we need to look at, well, what does it mean if it's not uniform? So here I've drawn another spinner for you. And I'm going to look at the probabilities of each of the outcomes. Again, we're looking at theoretical probability. The theoretical probability of red, I have 4 equal spaces here. Time 2 of them are red. So I'm going to say the probability of landing on red is 2/4, or I can simplify that and say that's 1/2. The probability of blue, I've got my 4 equal spaces on the spinner. One of them is blue. And my probability of green is 1 out of those 4 equal spaces. Since I have different probabilities here, the probability of red is 1/2, and then blue, it is non-uniform. All of them must be equal for it to be uniform. If any is different, it is non-uniform probability model. So what you're going to be doing today is you're going to continue practicing how we write probability models, how we find theoretical probability, and now we're going to add in the piece of, once you've done that, is it a uniform or a non-uniform probability?
Okay, so I hope that makes sense. I think the in between, it may have glitched for 1 second, but I hope it makes sense that when things have an equal chance of happening, it's going to be uniform probability. And when they don't, it's going to be non-uniform probability. There's not a separate special name for that. Okay, so let me share the screen here, and we'll just try a couple examples from our workbook. Actually, I'll put some on the board here, and I'll let you try them. Okay, so let's do this. Okay, so write yes or no to tell if each situation a uniform probability. Okay, so write yes or no to tell if each situation describes a uniform probability model. Okay, so number one, rolling one die. Okay. Flipping a coin. Number three, calling on a girl. And number four, a spinner with three stars and two diamonds. Okay. Minutes to do that. So write yes or no to tell if each situation describes a uniform probability model. Rolling one die, flipping a coin, calling on a girl in class, or a spinner with three stars and two diamonds. Okay, so work on that. I am going to, in the meantime, we're going to pull up our workbook. I don't know how this how the directions kind of glitched there for a second. I'm sorry about that, but that's very interesting that it did that. Okay, sorry about that. Okay, I changed the size of the screen and the wording went all over the place. Go figure. Okay. All right, so here we go. Here we go. How about rolling one die? Like the probability of one versus the probability 2, 3, 4, 5, 6. Be the same. Yes. So rolling one die is uniform probability. Flipping a coin, probability of heads is half, probability of tails and a half. So yes, it is uniform probability. Again, we're talking about an unbiased coin. So unbiased is what we're using. Unbiased, biased means that the coin could be somehow weighted to fall more on heads than on tails, but we're not dealing with that here. Okay, calling on a girl in class. Okay, here, you don't know how many girls and boys are in the class. There could be 3 boys and 5 girls, right? So probability of calling on a girl versus a boy can be very different. So it's not uniform probability. Okay, so there's no equal chances of the events occurring. And then a spinner with 3 stars and 2 diamonds. So the probability of stars going to be equal to the probability of diamonds. No. Okay, very good. Awesome. Okay, so now let's look at non-uniform probability. Okay, so now this is from our workbook on page 9. So I'm going to pull it up. Okay, and these are other probability models, it calls it. And other probabilities is just talking about non-uniform probability. So when an event does not have uniform probability, the odds of each particular outcome are not equally likely. So we already discussed that. Okay. When using the spinner that we see over here, okay, we could see that there is a greater chance of landing in the blue section than there is of landing in the red or the white section. So the chance of spinning a blue would be a half. So you could think of that as like that this half is kind of, that this piece of the blue here is kind of, let me just get this drawing on. It's kind of broken up. So there's two chances. There's four pieces. There's two chances of getting a blue, which is a half, one chance of getting a red, and one chance of getting a white, which is 1 out of 4. So it says below, for each situation, odds of all outcomes are equal or not equal. So we're going to think of odds as the chances of the events occurring at this point. Okay, so on number 1, are the odds of all the outcomes the same? So we'll try 1 together, and then I'll have you try it in 4 on your own. So there's 1A and 1B. On 1A, the odds are not equal. And in math, if you ever wanted to write not equal, you could write an equal sign with a line through it, not equal. That's like usually you use it between two numbers when they're not equal to each other. Like 2 is not equal to 3. On 1B, are they equal? Are all the outcomes equal? Yes, because there's 3 equal spaces and each a different color. So these are equal. Okay, so try 2, 3, and 4 on your own. 2, 3, and 4 on your own. That's that. So 2A and B, 3A and B, and 4A and B. So equal or not equal? Okay, so now let's go and let's take a look at what we did here. On 2, are the events equally likely? We have a 1, a 2, a 3, a 4, a 5, a 6. They're equally likely, so equal. But on the second one, when you look, you have 2 5s and you have 2 6s. So are the events equally likely? If you had 2 of the other ones, like 2, 2, and 2, it would be good. But you have a 1 and we have a 4, then we have 2 5s, and we have 2 6s. So not equal, not equal. Okay. What about if we flip a coin? You have a head or a tail. Are they equally likely of occurring? Equal. Very good. Okay, what about the spinner? So we have 2 1s, we have 2 2s, we have 2 3s. Okay, as long as we have the same, the probability will be the same. In other words, the probability of 1 will be 2 out of 6. The probability of 2 will be 2 out of 6. The probability of 2 out of 6. So therefore, equal. Okay. Are we doing okay? So let's take a look at number 4. Number 4. So we have a shaded in circle, and then we have the open circles and circles. So here there's a lot more dotted circles, right, than there are the other kinds. So this would be equal, not equal. Okay, and what about the last one here? It reminds me of like a trick-or-treat kind of bag, almost like a pumpkin face, right? But there's only 2 triangles and there are 3 squares. So if that's the case, it's not going to be equal. So not equal. Okay, so that makes sense. All right. So, and again, it says unequal odds, right? That's the chances of that event occurring. So unequal odds, it can be written as a fraction, which we've been doing. Nothing changed. So on the right here, you see spinner 1 and spinner 2. It says a game is being played in which the spinner and on a star to win. In spinner 1, we have 2 stars. So that would be 2 chances out of 6, or a third of getting the star. On spinner 2, we have 3 chances. So that's a little bit better. So 3 chances out of 6, or a half. Now, which one has the better odds of occurring, of getting a star? Spinner 2. Because so also you could think about it as comparing the probabilities, meaning 1/3 is less than a half, so the greatest chance of winning would be with spinner 2. Okay, you can also just use common sense with that. But again, you can compare the fractions or the probabilities. When we speak of odds, that's just the chance of the event occurring. So part of this will be your homework, and you'll be able to see, okay, if events are equal or if they're not, and then you can compare the fractions. Okay, so now what we're going to do is we're going to talk about empirical versus theoretical probability. Experimental versus theoretical. Now, theoretical is the one that we have been working on. And experimental is when so theoretical is what should happen. Toss a coin, you should get half heads, half tails. Now, we may do an experiment and we may toss a coin 50 times, but we may get only 40 heads and 60 tails. That could happen. Experimental probability can be a little bit different than the theoretical probability. And the theoretical probability experiment. So let's actually write that down. Okay. So we know, first of all, that the probability of an event is a number between 0 and 1, right? The probability of an event. Okay. Now we know that the theoretical probability is, so let's do this here. So the theoretical probability. Okay, and that we've already defined, okay, is, oops, draw. Okay, so it's the number of desired outcomes over the total number of outcomes. Okay, and this is the probability that we have been dealing with. All good. This is the one that we have been considering. Okay, now there's experimentality. So if we do an experiment, so experimental probability is based, let me just enlarge, okay, is based on a certain number of events that have been conducted in an experiment. Okay, so I'll give you a chance to copy that down. Okay, because again, we had said earlier, last week anyway, that the more trials we have when we doing are the number of outcomes in our results. Okay, so let's take a look at a video about this.
Experimental versus theoretical probability. When I think about theoretical probability, the one that you're most familiar with. Think about if I say, what's the probability for flipping heads on a normal two-sided coin? There's two possibilities, heads and tails. The probability of you choosing heads would be 1 out of 2. Theoretical probability is based on the math. It's based on the outcomes that you really can see that are on the coin, right? Now, technically, I have a theoretical probability of getting a flipping heads 1. An actual probability is what is expected to happen based on the math. When I'm thinking about theoretical probability, I'm thinking about what's the total number of possibilities or possible outcomes in these situations. How many of those outcomes would give me the desired event? So if I'm finding the probability of heads, I know that there are 2 possible sides on a coin, heads and tails, and I know that there is just 1 head. So my theoretical probability is 1/2. Just like I can find the probability of heads, that's 1/2, I can also find the probability of tails, which is the same.
Okay, so I stopped it here just in case you want to rewrite that again. We have that in our notes that the probability event is the number of favorable outcomes over the total number of possible outcomes. And that is our theoretical probability. Okay.
Same. Right? Again, I still have 2 options. Favorable outcomes or tails would be 1 out of 2 possibilities. This would be theoretical. Here's where it gets tricky and where we start to distinguish the 2. Experimental probability is when you actually start flipping the coin. So we're able to get heads 1 out of every 2 flips in theory, but you could have really bad luck, right? You could get tails over and over and over again. It could be a long time before you got heads, right? That would be where we get into experimental probability. Experimental probability is found by doing an experiment and observing the outcomes. We have a different equation for how we want to think about this. For experimental probability, we want to write our fraction as the number of times the event occurs out of the total number of trials.
Okay, so experimental probability, like we said, is found by repeating an experiment and observing the outcome. Found by repeating an experiment and observing the outcomes.
Let's go back to our flipped coin and look at this through the experience.
And so it's the number of times the event occurs over the total number of trials, which means if we only did 100 trials, there'll be 100 in the bottom of the fraction. And then let's say we got 40 heads, it'd be 40 out of 100. Okay.
Experimental probability lens. Let's say that I flip a normal 10 times in a row. Let's say that 3 of those times I get tails and 7 times I get heads. If I'm thinking about what's the probability for getting, let's say, heads, I'm going to think about that I flipped the coin 10 times and I got it 7. And remember, this is what actually happened to me. This is not based on the math. Based on the math, I had my probability of 1/2, right? This is based on what happened. So the probability of heads out of 10 flip would be that I 7. Remember, you need to simplify if necessary. I don't need to in this case. When I'm thinking about the probability of tails, in my case, I flipped it 3 times. So that would be 3 times out of 10 trials. 3/10 would be my experimental probability for flipping tails. Whenever I'm I like to think about what I hear in real life. So you'll hear people say, well, in theory, it should happen. That is based on the math, right? In theory, they're not basing that on what's happened to them. They're saying that based on the math, this should happen, right? If I flip a coin twice, I should get heads. However, experimental probability is what actually happens when I flip it. The denominator is based on the number of trials. So your experimental probability is going to look different almost always than your theoretical probability. I hope this video was helpful and you now know the difference between experimental versus theoretical probability.
Okay, so again, when she says in theory, right? In theory is based on that experiment. Let us do some problems from our workbook and compare the two. Okay, so let's go to our workbook. Okay, and this is page 15, page 15. So you can also get a lot of the reading out of here if you forget terms or whatever the case is, or you want to reread. Everything you could possibly want is in here. Okay, and then if you need more resources, I will definitely add them. Okay, so on number 7, it says compare the theoretical probability to the experimental probability. Express each probability as a fraction in simplest form. Okay. Allison rolls a die numbered 1 through 6. The results are shown in the table below. So technically, what should happen in theoretical probability, okay, not her experiment, not Allison's experiment, in theoretical probability, when we roll a die, okay, we should get the probability, let me change colors here, the probability of 1 is a 6. The probability of 2 is a 6. The probability of 3 is a 6. The probability of 4 is 1/6. The probability of 5 is 1/6. And the probability of 6 is 1/6. Correct? Okay. Our theoretical probability, right? So that's what we, in theory, think should happen. Okay, so what is the experimental probability of rolling a 6? Okay, so let's see how many times. So frequency is the number of times things happen. So when she rolled, she got 4 1s, 9 2s, 7 3s, 8 4s, 5 5s, and 3 6s. Okay, so if you don't know that, write that down. Frequency is the number of times an event occurs. Okay, so let's take a look at many experiments she must have done, because she got 4 1s, 9 2s, what we just said, right? Add that all up. The 4 and the 9 is 13, and the 7 is what? 20. Okay, and then over here she has 28, and then she adds another 8, 28, which is 36. So the total frequency here should be 6. Everyone agree? Did I do my math correctly? Is anyone checking me? So right, so we have the 13 the same, and then we have another 16, which is 36. So the experimental probability of rolling a 6, we have 3 of 36, which reduces to 1/12. 1/12. Well, what's the theoretical probability of rolling a 6. The theoretical probability, this was the theoretical over here. The theoretical probability was 1/6. 1/6. Okay. Probability is greater, and how much greater? So which probability is greater here? The theoretical, experimental. So now remember, we are putting in the simplest terms, but if you need help on this, right? This is 2/12, just to kind of compare them, right? This is 2/12 and this is 1/12. Which one was greater? The theoretical. Theoretical. How much greater? How much greater means how much bigger is 2/12 than 12. 2/12 take away 1/12 is 1/12, right? When you subtract fractions, you keep the denominator, subtract the numerators. Okay, great. So what is the experiment of rolling an even number? So let's go back to Allison's experiment. Rolling an even number. Okay, so we're gonna have to get this right off of the chart she has here. Rolling an even number, 2, 4, 6, right? Okay, so she has 9 2s, and she has 3 6s. So 9 and 8 is 17, and okay, is going to be 20. So getting an even number, there's how many possibilities of an even number? There are 20 possibilities out of 36. 20 possibilities out of 36. Okay, and then again, if they want this in lowest terms, something called the greatest common factor, which is the number, the biggest number, which goes into 20 and 36. It is. Okay, so if for some reason you don't know, just say to yourself, oh, they're both even, so let me first divide. Or if you know what it is and it happens to be 4, you could divide by 4 first. But let's say you didn't and you divided by 2, right? So you would get 10 out of 18. And then if you divide it by 2 again, you would get 5 out of 9. 5. That makes sense? Okay. Now, starting to run out a little bit of room here. So this was 20 out of 36. Let me put this in with a little text box here. 20 divided by 36. Okay. So now probability, the theoretical probability of rolling an even number. Okay, that's the probability of getting a 2, a 4, a 6, which is a 1/6 over here. Whoops. 1/6. Doesn't want me to write 1/6, 1/6, and 1/6, which all together is 3/6. 3/6 is equal to 3/6 or 1/2. That makes sense? Okay, now it's saying how much greater. So now you have to compare the fractions. You have to compare the fractions. So you're comparing 5 out of 9, right, to or 20 out of 36 to 3 out of 6. However you want to do it and get a common denominator. Lots of people know different tricks when comparing fractions. Like, so for instance, if you have half here, or some people just know by common sense, right? But again, I don't want to rely on that because let's say you don't, it's okay. There's a half, right? And here's 5/9. You can compare if you cross this way and put the 9 here, cross this way and put the 10 here. that 5/9 is bigger than 1/2. Has anyone ever done that? Comparing fractions, right? Also, you could just take your calculator if you want. You could change them to decimals, whatever you feel more comfortable with. Okay. So which probability is greater? In this case, the experimental is greater. The experimental is great. Experimental is greater. And then how much greater? What we're going to do is we're going to 5/9. Now, again, what you may just want to do is you may want to, however you want to do it, if you want to do it in your calculator, minus 1/2, right? So if you want to grab a calculator and do it that way, you could do it that way. If you want to use the here, the 20/36 and the 3/6, because they're friendlier with the denominators, whatever makes you happy. So it's 5/9 minus 1/2. Okay, because again, I'm not going to be a judge of how you learn that math. Okay, so minus 1/2. I'm going to get a common denominator of 18. So 10/18. And this is 5/18. That should be, sorry. There should be an 18 down there. Oh, sorry. This should be an 18. So this should be 9/18. My little eraser. Okay, here we go. Okay, so 5/9 is 10/18. 1/2 is 9/18. So it's 1/18 greater. Are we good with that? So when it says how much greater over here, okay, and I'm sure everyone has a method for doing this. If you just need to use your calculator, that's okay. Right now, no judgment zone here. Okay, awesome. We're doing great. Okay, so now let me just stop the share for this. Okay, so how can we find out how many outcomes can occur? How many outcomes are in a sample space? Okay, so we talked about this before. I did mention something about the counting principle. Okay, this was from week 1. And I had said if one event can occur in M ways and it can occur in N ways, then they can occur together in M times N ways. We multiply that together. If you look back, it should be in your note. We're going to go over it again. I'm a big fan of trying to incorporate the lessons and kind of just have them together so that the math becomes like part of us, right? Okay, so let's take a look at a cute video about the counting principle. Attention to in this video is at the beginning of it, they said you go shopping for some new threads. So some new threads, new like duds, some new clothes, right? So it's like it's a fun way of saying you're going shopping for some new clothes. Okay, so here we go.
Let's say that you go shopping and you're looking for some new threads. You want to get a shirt, shorts, and some shoes. And what do you know? Your favorite store just happens to have a sale going on. Get a shirt, shorts, and shoes for $49.99. They have the shirt you want in 7 different colors, the shorts you like in 4 different colors, and some cool shoes in 5 different colors. And because you're a stats nerd like me, you want to know how many different sequences of the 3 are possible. To answer this question, we can use the fundamental counting rule or principle, which mathematically says in a sequence of n number of events, where the first K1 number of possibilities and the second event has K2 number of possibilities, and so on, the total number of possibilities of the sequence will be K1 times K2 times K3 times ... Kn.
Okay, so don't worry about that notation. If you understand it, that's great. You're multiplying the number of possibilities of each event occurring. So I'll do another example of this at the end if he doesn't.
What this is saying in simpler terms is that when you have a certain number of events, like in our example, shirts, shorts, and shoes, to find the total amount of possibilities of the sequence, number of ways one event can occur, times the number of ways the other events can occur. So 7 different colors for the shirt, 4 different colors for the shorts, and 5 different colors for the shoes. When we multiply them together, 7 times 4 times 5, we get 140 possibilities of the sequence. To show this visually, here is a tree diagram for a coin flip and a die roll. You can have a head or a tail on the coin flip and a 1 through 6 on the die roll. As you can see on the right, there are 12 possible outcomes. Using the fundamental counting rule with the coin flip as event 1.
Okay, so we're about to do some tree diagrams, and let's just see how our timing is doing. Okay, yeah. So we're gonna quickly touch on tree diagrams today, but not go into a whole lot. However, and this looks worse than it is. It's not that bad. What you're seeing is there's 2 possibilities on the coin, 6 possibilities on the die. 2 multiplied by 6 is 12.
1, and the die roll is event 2. We have 2 possibilities for the coin flip and 6 for the die roll. So 2, same result as the tree diagram. One more example is a 4-number PIN code for a credit card. Numbers 0 through 9 can be used. So 4-number code means 4 events, and 0 through 9 means 10 possibilities for each event. 10 times
10 possibilities because 0 to 9 is 10 numbers. Yeah, everyone always gets confused. Like, that's only 9 numbers. It's 10 numbers, 10 numbers.
10 times 10 times 10 equals 10,000. So 10,000 possibilities of the sequence. All right, my friends, hopefully this video helped you out. I do have more videos right there for you.
Okay. And so do I. Lots of fun stuff headed your way. Okay, so let me put up problem on our board here that you could try on your own. Okay. All right. I'm gonna put this up here. Hold on a second. All right. So let's have a possible question that you can get. Okay. So you go out to a restaurant. There are 5 main courses. Let's start with appetizers. I love appetizers. There are 5 appetizers, 4 main courses, and 3 desserts. Not deserts. Deserts is with 1 S. Desserts is with 2 S's. And speaking of that, something that's really cute that I love is the word stressed, spelled backwards is dessert. You see it? Desserts. It's so whenever you're stressed, have a dessert. That's what I do. Okay, so I'm sorry to get off track, but yeah, desert is with 1 S. Dessert is with 2 S's, and dessert spelled backwards is the word stress. Stress spelled backwards is the word. Okay, so here we go. Let me just keep going. Now I'm hungry. There are 5 appetizers, 4 main courses, and 3 desserts. Okay, there should be a period at the end of that. Okay, so let's go over here. How many different meals? Okay, how many different meals consisting of 1 appetizer. My math is better than my typing. Yes. Okay, 1 appetizer, I'm glad I keep myself entertained. 1 main course and 1 dessert. Okay, so how many different meals consisting of 1 appetizer, 1 main course, and 1 dessert? Okay, so I'll have you copy that down. And so these are very, very straightforward kind of questions that they give you. And again, we are going to more about tree diagrams. We'll actually do that next time because I actually want to show you something that happens with the counting principle as well. A little something they can tweak the problem. Tweak means change it a little bit, okay? But how many different meals consisting of one appetizer, one main course, and one dessert? Okay, so how many appetizers are there? There's 5. How many main courses? There's 4. How many desserts? There are 3. So 5 multiplied by 4 multiplied by 3 is how much? So 60 possible meals. Okay, now sometimes it can get tricky. So let's say they say something like this, and I'm not gonna go out of my way to trick you, but it's all about the reading, right? Okay, so how many different meals consisting of 2 different appetizers, 1 main course? I'm not going to make it that tricky. And 1 main course and 1 dessert can be made. Okay, now you may say, okay, I don't know why this is tricky. The reason why this is, can anyone tell me? Okay, let me see if I can highlight it here. 2 different appetizers, 2 different appetizers. Okay, so that means that when we write out our possibility, text box in the drawing today, it's not jiving with me. Okay, here's our first appetizer, our second appetizer, our main course, our dessert. So different appetizers, meaning I can't have 2 of the same appetizers, even though sometimes I want to, yeah. Okay, so how many appetizers for the first, can I pick first? So 5. But then I can't pick the same appetizer twice. So let's say I pick mozzarella sticks. I have to pick something else. 4 possibilities left because I took away the mozzarella sticks. Okay, so those are the 2 appetizers. Then a main course, I go back to 4. This is the main course, 4 main courses, and 3 desserts. Okay, so again, this was the appetizers, the main course, the dessert. Okay, so you see how that's a little bit different? So in this case, it's going to be 20 times 4, right, which is 80 times 3, which is 240 possible meals. Someone's really hungry here. Possible meals. Okay. Okay, so I'm going to leave you with a little video that kind of summarizes a lot of what we did in a fun way. Okay, here it is. It's kind of cute. I really like it. And take a look at the spinners on each of the people.
It was sunrise at the crossroads, a glorious day to see, when a cowpoke came riding up on a horse and looked down the road called 3, stopping to someplace else. In probability, it was likely, yes, though it wasn't for sure, that this cowpoke could spin through. The sun climbed up to high noon. Another cowpoke said, gee, with an outfit like mine, it's unlikely I'll visit 3. A dry wind whistled. The cowpoke spun. Let's be on the safe side. But the answer was clear. This lone cowpoke down the someplace else road would ride. Then later that same afternoon, one mule from a mule team clomped in. One look at this cowpoke would make it quite clear that 3's an impossible spin. The spinner all day and all night. But one thing was easy to see. This cowpoke was headed to someplace else, but never to 3. As sunset arrived, one last cowpoke rode up a strong horse's back. The chances that 3 on the spinner would be were certain. And that is a fact. Impossible clearly was not a word this cowpoke would ever use. A few quick spins made sure that 3, the only road to
So I hope you enjoyed that. And don't forget to hand in the homework. Homework is always due by midnight on the Sunday before the next class. So you have plenty of time. It's not a lot. I will post it. Again, just submit it. I'm not checking for accuracy. There is an answer key of the book. Okay. And that's when you could check your answers. And if you ever have any questions, you can email me about them. I'll show you next week where the answers, but if you just scroll through the whole workbook that I have for you, the answer key is right at the end. There's no explanations for some of them, and that's reach out to me and ask me. I'll be more than happy to help you. So have a wonderful week. Be safe, be well, and I'll see you soon. Bye.